Hello everyone, welcome to the lecture series on Foundations of Deep Learning, Concepts and Applications. Today we are in the last theoretical session of the week 10, where we have started with the autoencoders and variational autoencoders. In the previous session, we have seen the limitations of autoencoders and how these limitations are overcome by using a variational autoencoder, and under variational autoencoder we have seen the architecture and then the loss function. And continuation in today's session, we will see reparameterization trick, one of the most important concept of VAE, and let us understand this and then the math behind this. So, a quick recap of what exactly has happened. We have a loss function. The loss function has two terms. One is this is a reconstruction loss, reconstruction term. Here, if at all, if you are using a mean square, if it is a continuous data, then it is a mean square error. If it is a mean square error, you will have this formula in terms of MSE. If you are if the aim of decoder is the binary data, then this particular term will take a binary cross entropy form. Yeah, and the second part in loss function is KL divergence, and what KL divergence does is, here the latent Z is the latent space, this is the probability distribution of the latent space, and here we are assuming this to be a normal distribution with the mean 0 and variance 1 or standard deviation 1. Because of this, from input only we get the latent space. So, input is forced to take the Gaussian form, and the Gaussian form will be having a parameters mu of x and then the variance square of x. Now, this is what are the parameters. This is what has been written here. So, in a closed form, what do you mean by closed form? Where you can put the values and then solve it. So, this here you cannot get, you do not have any formula here. Therefore, this same term can be represented in this form. This is what is the loss function. What exactly is the problem here in VAE is, look at this particular reconstruction, or look at the overall loss function. We have Z and Z is sampled from this part, right. We have already seen from our previous session, Z is sampled from this. Encoder is the one which is learning these parameters. So, once these parameters are known, then Z is sampled from these parameters. Now, since Z is an random operation, the meaning of sampled is randomly drawn. When Z is randomly drawn from this using these distribution, random operation always blocks the gradients to flow. If the gradients are not flowing, if you are not able to compute the gradients, if you cannot, if the gradients does not flow, then how is that we can update the parameters, learnable parameters. Therefore, in order to solve this particular problem, what I have explained is written here. So, in order to solve this particular where backpropagation cannot pass through randomness, in order to solve this, we have a concept called reparameterization trick. So, let us understand. We will also see the backpropagation, how it is propagating, and then we will also see a reparameterization trick. So, when you see once you get the reconstructed data, reconstructed value, and then when you backpropagate it, when you backpropagate here. So, from Z when it is passed to a decoder, decoder is going to get a reconstructed data. So, now whatever the data that we have got, you are going to compute the loss between these two. You will compare, you will compute the loss. When the loss is too much, you will backpropagate it. Now, what are the learnable parameters at a decoder? So, once a decoder outputs the distribution, then this becomes a normal neural network. So, the decoder parameters are, if it is a fully connected neural network, or if you are working on if X is a simple CSV file data. So, if your aim is to construct those tabulated data, then decoder is a simple fully connected neural network. In a fully connected neural networks, what are the learnable parameters? Is it not the weights and then the bias? Is it not you will write weight multiplied with the values plus a bias, and that is computation at h, and then you will get this x as some function of whatever is this h. This is how you will compute the calculations. Now, once you do these calculation, here what I am trying to explain to you is the learnable parameters here are the weights and bias. So, for a fully connected neural network, so when Z is passed to a decoder, and decoder will output the parameters, and those parameters depends on what kind of data the decoder wants to produce. Now, once the decoder produces those output parameters, then here the learnable parameters here are the weights and bias if it is a fully connected neural network. Suppose if you are working with the images, then here the learnable parameters are at an it can be an kernels, convolutional kernels, it can be a bias, or if you are using a batch normalization, those parameters. Therefore, now if you assume weights and bias are the learnable parameters, how do you calculate, how do you compute? So, it is derivative of loss with respect to W and derivative of loss with respect to bias is what we need to calculate. How do you compute this? How do you write? So, once you get, you are going to calculate the loss. Once you get the reconstructed, you will calculate the loss. So, it is derivative of loss with respect to x, then derivative of x with respect to W. So, that is what is being written here. Similar way, derivative of loss with respect to this x, and from x you can reach to the bias term. So, this is how you will compute the gradients at a decoder side. So, once Z is sampled, decoder behaves like a normal neural network. So, based on what kind of neural network that we are building, accordingly we are going to have a learnable parameters and we are going to compute the gradients. So, here there is no problem at all. Now, next what we are going to do, so we have back propagated and we have completed this part. Now, from here we have to look into the Z. So, how will you compute this? How are we writing? Derivative of loss with respect to Z is written as, you can reach through x only. So, derivative of loss with respect to x, then x with respect to Z. So, this is how we are writing, we have written mathematically in this way. Now, why is that we have written like this? Now, when you look into this, Z is just a numerical, it is a vector, right? Once you sampled Z from that mu and variance, once Z is sampled from this, Z is just an vector. So, which means decoder is differentiable with its input. Therefore, the gradients flow even here as well. Now, where exactly is the problem? So, look at this. The problem starts when the gradient actually reaches Z. Now, the gradient have reached to this particular point Z. So, the problem starts here. Why do you think the problem starts here? How are we getting a Z? Is it not Z is sampled from this distribution? So, we are obtaining a Z by randomly drawing from a distribution. Now, distribution meaning which distribution? Parameterized by mu and variance. So, you have Z sampled from this, which is having the parameters mu and variance. So, it is variance square. So, we can write, let me erase. So, there is an error in the representation. So, it is variance square. Yeah. So, this is how variance square of x. Yeah. So, z is sampled from this particular distribution. When z is sampled from this, then what are the parameters we have? The parameters here are mu and variance. So, we need to compute a derivative of loss with respect to mu and a derivative of loss with respect to standard deviation or variance. So, using a chain rule, how can we write? How can we reach up till this term? Is it not you can derivative of loss with respect to z first? You will reach it to z, and from z you can reach it to mu. Then derivative and this term is written it as derivative of loss with respect to z and z with respect to variance. So, this is how we are going to write the formula. We are going to write the this is how we compute using a chain rule. Now comes the question, the issue is actually lying here. Now, you can ask the question, what is an issue? What is the problem here? Because it is randomly drawn. We do not have a particular formula that calculates this z. Z is randomly drawn from this particular distribution. Therefore, the sampling operation is not a deterministic function. What is a deterministic function? You will see that in a while. So, sampling operation is not a deterministic function of mu and variance. Therefore, this d of derivative of z with respect to mu and this particular term are not well defined, meaning there is no fixed rule which tells us how much this z change when there is a change in mu and sigma. So, mu and variance, not sigma, I am sorry, mu and variance. So, how z changes when there is a change with respect to these parameters? So, we do not have a fixed rule, there is no well defined form, because z is randomly drawn, not by any formula. So, let us understand this with an example. If z is sampled from this, now imagine mu value is 1 and then this variance square value is variance is 0.5. So, now if this is 0.5, this square is 0.25, that is what has been written here. So, mu is this and square is 0.25. Now, sample z, multiple times you sample it. So, when for the first time when you sample, z value what you have got is this. Second time when you sampled, the z value what we have got. Third time when we take, what is sampling? Z is randomly drawn from this distribution. We are getting this. Now, when you look into, now the question, there is one question to the learners here. What is derivative of z with respect to mu? Do we have an answer for this question? There is no answer, right, because here mu did not change, this did not change, but z, there is a different values for z because it is randomly drawn. Each time when you draw, it is a different value. So, this is what is written, mu did not change, this did not change, but still z got changed. Therefore, derivative of z with respect to mu is undefined. This is what, it is not a deterministic function of mu and variance here. So, where exactly the problem is? The in a single line the problem is here. Because of this, we doesn't know the value of these two terms. When we doesn't know the value of these two terms, how can we compute the values, correct? Now, how do we solve it? So, how can we sample z in a way that the gradients actually flow back? What is the derivative of this term? How can we compute these two? So, how can we answer this? So, now instead of directly writing that z is being sampled from n, so rather than writing in this way, problem is exactly in this formula only, z is sampled from this distribution. So, instead of writing a z in this way, can we randomness, there is a randomness in this formula. Why there is a randomness? Because z is randomly drawn from this particular distribution. So, can we generate z using a formula where randomness is independent of mu and variance? Can we write in this way? So, by rewriting z where randomness is totally independent of these two terms, if we can achieve that, or if we can write z in that way, so is it not randomness will no longer block the gradients? In that case, backpropagation actually works here. This has led to a concept called reparameterization trick. So, this is called reparameterization. What exactly is the reparameterization? Now, see, you are earlier z is sampled from this mu of x and variance. This is how z is being sampled. Now, you are writing z as mu where this is drawn from a normal distribution having a mean 0, variance 1. So, can we rewrite z in this particular way? Initially we wrote z like this, now we are writing a z in this formula. Now, you can ask the question, what exactly have we achieved by writing this? Is it not now, where exactly is the randomness? The randomness is this term. Okay. So, this is what is the randomness. Now, randomness has become independent of the parameters. Now, with this the gradients the gradients can flow back. We will see that. Now, there is one question to learners here, because your aim was to remove the randomness, or is it the aim, what was the aim? Aim is to remove the randomness, or aim is to move the randomness away from those parameters? Answer is move away. Now, you can ask the question, what if you remove the randomness? If you remove the randomness, this becomes a 0. When this becomes a 0, z is just this. When z is only this part, it becomes autoencoder. The model becomes autoencoder. Then, why do we require one more concept called VAE? So, the whole concept of VAE is to generate new samples. In order to generate new samples, compulsorily randomness has to be there. That is where we have written this term. Now, the whole intention here is randomness is still there, but we have moved randomness a little away from the parameters. So, that is the reason we have written z in this way. Now, once you write this during a backpropagation, anyhow this term becomes a constant. Therefore, the whole intention is you can able to backpropagate here. Now, because this is just one constant value, when this is a constant value during a backpropagation, this term becomes 1 constant. Yeah. So, now take this particular z and then differentiate. The whole problem before was derivative of loss with respect to mu and derivative of z with respect to mu and derivative of z with respect to variance. This was then before. Now, look at what exactly when to this particular formula, when you take a derivative with respect to mu. So, is it not you will write in this way, derivative of this term with respect to mu. So, we have written this. Now, this term, is it not the first term is 1, because derivative of mu with respect to derivative of mu is 1. And since here there is no mu term, this whole becomes 0. Therefore, we have an answer for this. Earlier we were not knowing what exactly is the value of this term. We were not knowing this. Because of this the whole problem occurred. Now because you have written Z in this particular way, where randomness is moved a little far away or little away, you can able to now get the value for this. What is the value? The value is 1. Okay. Now let us see how do you differentiate with respect to variance. So how will you do it? Since you do not have, this term becomes 0, and here the term is mu does not depends on, so therefore the first term becomes 0, and anyhow we know that this is a constant. Therefore we have an answer even for this term. Earlier derivative, this term and this term was undefined. Now we have an answer for these two. We have a value for these two. Therefore the chain rule, which was a problem in the previous slide, derivative of loss with respect to mu is written as derivative of loss with respect to z, z with respect to mu. And since we know this value, now what exactly is this? Is it not this term? Similar way, here earlier we were not knowing this value, but now it is an constant. So we have an answer for every of these terms. Therefore there is a normal flow of gradient. Now this is called a reparameterization trick. What is a reparameterization trick in short? When you sample Z from a normal distribution, so there is a randomness. Because there is a randomness in the operation, the gradients does not flow. When the gradients does not flow, how do we compute, how do we update those parameters? Therefore instead of writing a Z in this way, we are writing a Z using this term. We are writing Z like this. Now in here what exactly is happening? The whole intention is not to eliminate randomness. The intention here is move the randomness independent of the term. So therefore we have written Z. So because Z is written like this, we can able to differentiate Z. Look at the way that we have differentiated it. So because Z is written, Z is taking this form now, we can able to get the values for these two terms. Because we got the values, now derivative of loss with respect to mu and with respect to variance you can able to compute. Therefore there is a normal flow of gradient. Because of this is the final architecture of VAE. Earlier we had just taken the input, that is passed to an encoder. Encoder used to give mu and variance, and from this Z is being sampled, that is passed to an decoder, and you were getting a reconstructed data X. But now how we are doing, it is just not mu and Z, I mean mu and variance, you also have an this term. So this term will help for back propagation. So earlier the original, this is an original encoder and variational autoencoder. So you have just these two terms, but now you also have this term. Because of this, during back propagation, the gradients actually will flow. Here the gradients were not flowing, but here the gradients will flow. With this we have come to an end of the theoretical session on autoencoders and variational autoencoders. That is the last session on of our week 10. In the upcoming session, in the next session, we will see the hands-on implementation on autoencoders. Thank you.